Hello and welcome to this video. In this video we're going to be looking at the topic of moments. So what we're going to see is that when we have these forces, what we've looked at so far is that if I apply a force to an object, the object will tend to move in the direction of that force. Okay, so I know if I start with some block and I apply some force F to it, I know the block is going to move in this direction as long as there's no other forces present. But sometimes things don't always move in the direction that we push. So let's take an example of, let's do a door first. We'll start with a door. Imagine this is a top-down view of your door, and this is your hinge on this side. Okay, so your hinge is connected. When you come to the door, you see that you have the door handle here, and so in order to push this door open, assuming it's a push door, we push it that way. But its actual motion, which I'm going to do in a different color actually, its actual motion is going to start to curve around. Okay, how do we explain that? Why does that happen? Well, logically we know it's because of this pivot point. Okay, so we call this the pivot here. Okay, but what makes it how would we be able to quantify how that arcs, or how much force would we have to put in order to make it arc in this way? Okay, and this is what a moment is. So we know forces can act in order to make something go in what we would call a linear direction. So if I apply it in this line, it travels in this line. We can also get circular motion, and this is another topic we're going to look at at the end of your AS exam. So it will still be in your A-level paper 1, circular motion, but it would technically be after you've covered all the AS content. Okay, so this is moments. Now some of you might have met moments before, and you would know that in order to calculate what the moment is, we would say it's the force applied multiplied by the distance. So this distance here, let's call this d, so the perpendicular distance from the pivot point. Okay, now this is a very long-winded way of writing it down. I could actually just write it as it's shown in your formula sheet, is moment is equal to FD. Okay, now D is distance. Okay, I haven't written displacement. It doesn't matter what direction you are away from the pivot point, it just matters that you are some distance away. But F, we know, is a vector, so that means moments are vectors. Okay, but in terms of the direction, it really depends if we're going to push or pull this door. If we push it, it will travel anti-clockwise. If we pull it, it will travel clockwise. And so it is going to be a vector quantity because it does matter what direction we apply the force. So if we were to apply the force downwards, it would go this way. Okay, and this is how we would quantify a moment. So we'd measure moments. Since we're doing a force which is measured in newtons multiplied by a distance, we would say the moment is measured in Newton meters. Now, why does this help us? Okay, well, we can start off by doing a little experiment. You can pause this video and you can go to your nearest door and try pushing it at the handle here to open it, and you'll find that it will be quite easy. And then try pushing it really close to the hinge, as close as possible, and you should find that you'll have to put in a lot more force to actually be able to cause the door to shut or open, depending on what you're doing. And this just reinforces this whole idea. Okay, this is essentially saying that the force is inversely proportional to the distance. So the closer you are, so the smaller the distance, the bigger the force has to be in order to produce the same moment. Okay, if you're your distance is very large, then your force doesn't have to be large, and you'll produce the same moment. So you can imagine that the moment it takes to actually open your door is fixed, okay, because that's going to be essentially based off how strong your hinge is, or how much force you need to be able to open or close the hinge. So the moment will be fixed, but the amount of force you apply depends on the distance. Now this will come in handy for most things. You can, for example, if you ever felt like trying to open a door from like right next to the hinge, you now know that's not a good idea. If you didn't already, you probably did. But also things like paint pots. If you're ever doing some home decoration, and if you've ever tried to open a pot of paint, you'll find that they have quite a difficult seal to open, and you have to kind of get something under it and push it up. And if you're going to do it with your fingers, it's going to be quite difficult. But if you get a screwdriver, this becomes your pivot point. So I'm just going to start calling the pivot point P, and your screwdriver has some distance for you to apply some force. And now you'll apply the force downwards, and that will cause this to go upwards, and then the paint pot pops open. Now, if this is your force and your distance is just the length of this, that means that the longer, or the force should technically be perpendicular as well. So let's put it there. So the longer the screwdriver, the easier it will be to actually open this paint pot. The same way that the longer the distance between the force that you're applying and the pivot point on a door will make it easier to open or close the door. Same with the paint pot. Okay, so we can use some practical applications for this. But we can have other things. Another thing that would travel in something of a circle would be something like a seesaw. And this is where we start transitioning from just having one pivot point to now having, or a pivot point on the end of something, to having a pivot point in the middle. Okay, so now let's look at some examples of a seesaw. Let's say we had some line here, and this is the seesaw. This is your pivot point P, and we know that if we put masses on the end of the seesaw, this mass, if we say that this distance is equal to this distance, so they're both a distance d apart, and let's say that this mass m is the same as this mass m, that will produce the same force, so they'll both be F, but this mass over here is going to produce a moment that travels anti-clockwise, whereas this mass over here is going to produce a moment that travels clockwise. So what's going to happen to the seesaw? Well, we know from logic, if we were to apply some logic, that if we have the same mass on both ends of the seesaw will just remain horizontal. Okay, so the seesaw remains horizontal. And this is because of something called the principle of moments. Okay, so this is another thing we can look at in order to work out moments. Sometimes we don't want things to turn. Sometimes they'll have pivot points, but we want them to stay the same. For example, if you had a shelf, if you had a shelf and you put a single support beam under the shelf, that would act as a pivot point. And then depending on what you add to either side of the shelf depends on if the shelf is going to remain horizontal or it's going to start to tilt to one side or the other. So we can use this idea of moments to try and put things under the center of mass of this system, and that's going to help it to stay in what we call equilibrium. Okay, so this remaining horizontal means that it stays in equilibrium. Equilibrium is where all the forces, or in this case all the moments, balance, so there is no resultant motion. So this stays in equilibrium. Okay, and that brings us on to the principle of moments, which says that if the total anti-clockwise moments, so we add up all of the anti-clockwise moments, or the sum of all the anti-clockwise moments is equal to the let's be consistent, to all of the clockwise moments, clockwise, just one word, to all the clockwise moments, the system is in equilibrium. Okay. Now this is going to prove to be probably the most useful bit of information, because most of the questions will either ask you to recite this or to use this to try and calculate some forces or something like that. Okay, so let's do a very quick example of that. Let's say we had something very similar to a seesaw. Let's say we have a plank here, and let's say we have a pivot point that's not in the center. Okay, let's have a pivot point here such that it is let's say 1 meter away from the very edge, and on the very end we're going to place a mass, and this mass has a mass m, and then at some distance, let's call it d away, we're going to place another mass, but this mass is actually 2m. And the question might ask, what does d have to be in order to maintain equilibrium? So it will tell you the system is in equilibrium. I'm going to simplify equilibrium to just EQ, and then what is d? What is the distance d? And now what you have to remember is this is going to cause some sort of anti-clockwise moment, and this is going to cause a clockwise moment. For them to be in equilibrium, they have to be equal. So m times 1, so the force is going to be actually mg here, and the force over here is going to be 2mg. So mg times the distance, but the distance is 1, so I'm just going to times this by 1, which means it's the same, is going to be equal to 2mg multiplied by d. Now in order to actually calculate what d is going to be, we could cancel out this whole mg, so that means that 1 is equal to 2d, and therefore we could say that d has to be half a meter. Okay, so we'd have to put d we'd have to put this 2m closer, such that it's only half a meter away in order to make this in equilibrium. Okay, now this is a very simplified example. They can add any amount of objects on this plank, but it would be the same. We would just have a linear addition. So if we had maybe another mass here, we would say this is just mg times the 1 plus, let's say this is m prime times 0.5 is equal to, and then the sum of all of these anti-clockwise moments or clockwise moments. So the principle would be the same. You would just add up all of the anti-clockwise moments, set it equal to all of the clockwise moments, and then solve for whatever they're asking you to solve for. Okay. Now another thing they might ask is to identify something called a couple. Okay. Now a couple is a very specific case of moments. Okay. So couples. Let's take a physical example first, and then we'll see what's going on. So the physical example that we can obtain would be something like a steering wheel. Okay, so imagine we have some sort of steering wheel here, and the center of this is your pivot point P, and one hand is over here, and you're applying a force F up here, and your other hand is here, and it's pulling down with a force F here. And let's say this has a radius R. So the distance between them is the same. Okay. Now, both of these moments, although they're on opposite sides of the pivot, are both anti-clockwise moments. So both of these things are actually contributing to be the same thing. So a couple is when two forces create, or we should say two equal forces to be specific, two equal forces work together to create circular motion or rotational motion, to create a rotational motion. So hence, what we can tell from this is that the wheel is going to start turning this way because we're pulling up, which means we're going to start rotating the wheel in this direction. Now the idea for this couples is a little bit different. Instead of actually just taking the distance from the pivot, we want to actually take the distance between them. So for couples, the moment is actually equal to the force of just one of them. So I'm just going to use F multiplied by the distance between the lines of action. Now, what do I mean by lines of action? A line of action is just the direction that the force travels in. So this would be, I could extend that down. That would be that line of action. This would be that line of action. So it just, the force is applied in this general line. So we're just looking for the distance between these two lines, which we know is just going to be r plus r. So it's just going to be 2r. So in this case, the total moment acting on this steering wheel is just F times 2r, or 2FR. Now, this idea that we have to change this distance seems like we're making things a bit more complicated at first, but actually this is just a simplification. This, I would say some teachers will say that you have to use this distance between lines of action, but really it's completely your choice. Whether we do using the distance between lines of action, or we just add these two separate moments together, they'll both give us the same answer. So if I said I just want to look at each individually first, then the force from this one is F, and the distance to the pivot is R, so the total moment is just FR. And then of this one, it's the force is in the opposite direction, but the moment is in the same direction, so I can add together another FR, and we just get 2FR, okay, which is exactly the same as what we get here. So whether you do it via the force is equal to distance between the lines of action, or just add together the two moments acting in the same direction, you'll get the same answer. So it's really up to you which one you prefer using, or which one you're more comfortable with using, but both should give you the same thing. Okay, now one final thing that we have to look at is just how do we bring in Newton's laws into this? Because surely we have forces, Newton's laws have to behave. In terms of having a overall resultant force or anything like that, we're not really going to get any resultant forces in a specific direction. We'll have resultant moments in order to cause things to rotate, but the force isn't necessarily going to be specific, but the reaction forces will come into this. So if, let's say we have a beam again, but in this case we're going to have two pivot points. If we know that this beam, or even let's put some masses on this beam, let's put some over here and let's put one in the middle, let's say they're all equal masses, for example. If let's call this pivot point A, and let's call this pivot point B, because we could pivot about either of these points, and we could solve for the moment about either of these. And for the most part, most questions will ask you to solve around each of them individually, and that will give you all of the answers you need for that question. So what we would do is we'd have to choose first, do we solve from A or from B? So let's say we solve from A. If we solve from A, then what forces do we actually have? What rotational things do we actually have? Well, we have this mg from here, and this mg is going to cause some rotation in the anti-clockwise direction. Then this mg here is going to cause some in the clockwise, but this is also mg, and and you'd have to add these together, and we know this distance here is much bigger than this distance anyway, but both of these moments combined is going to have a massive rotational force. And so what they might ask is, how would this ever be in equilibrium? And it's because of this reaction force here. If this whole beam is pushing down on B, it means B is also pushing up back on the beam. So there's also a force up here, which we're going to call FB. And that's going to cause some rotational force there. So really, if we were to solve this, we would have to say that we'd have FB times whatever the distance from A is, plus the mg times whatever the distance from A is, must be equal to this mg times whatever distance that is, plus that mg. And that's what we would solve. And most of the time they're going to ask you to solve for this FB. As soon as we've solved for that FB, they'll also ask you to solve for FA. Now solving for FA is a little bit easier, so you'll usually get 3 or 4 marks depending on how many things are on this beam for solving for the first one. But solving for the second one, you can just what's called resolve forces vertically. If we know the whole thing is in equilibrium, there's no resultant force anywhere, and so that means that the total force is acting down, which is essentially just 3 mg, because we have an mg here, we have an mg here, and we have an mg here. If we add them all together, the total force coming down is 3 mg, and then assuming that this rod has negligible mass, but the total forces going up are Fa plus Fb. And you could just use this idea that if we have the force at A and the force at B equal to 3 mg, and we know the force at B, we could just solve for Fa that way. So there are always different ways that you can look at it. So we can either, when we have these moments, we can either resolve by looking at the moments around them, and sometimes we can even just resolve by saying that the forces in the vertical direction have to cancel out in order for this to be in equilibrium. And this is everything we need to know about moments. I will say as a forewarning, don't just rely on this video to be able to do all of these. Everything in mechanics is maths based, so it's going to require a lot of practice. While all the content that you need will be in this video, you're not going to just get the grade by watching these videos. You have to go and practice. Physics is applied knowledge. You have to take all of this and now go and do loads of practice questions and see how they would actually apply this in questions. And I feel like that practice will help you the most. Not just in mechanics, but in all topics. Practice questions are probably the best way to go about it. But especially for this section of mechanics, and to be fair, most sections of mechanics, because they are very maths based, so they require a lot of practice in order to solve all the different problems and be able to see the similarities and what the question's actually asking you to look out for. Hopefully this all helps and makes sense, and thank you for watching.